Okay, so the final thing we'll look at on the basic side is what authentication is providing for us. So I mentioned before in the overall list non-repudiation, right? So non-repudiation actually combines two things at once. It combines the integrity of the transaction. So we talked about how we can validate the integrity of something, right? We were looking at files, but we can validate the integrity of any chunk of data with those methods. But we also need to authenticate the user that was performing the transaction. So we're going to look at authentication in sort of a general terms here, because we're going to look at more than just user authentication. You might have heard of authentication probably from websites at minimum, right, where they have authentication methods like passwords. We now have two-factor authentication, where it's trying to say, do you have two different ways of showing that you are who you say you are. But often what we'll talk about with this is not necessarily saying we need to validate the exact user, but we want to validate often that the user has some knowledge of a secret key. Right, so often what we're going to look at is not, validating a user accessing a server, but validating that a firmware update file, for example, has been produced by a trusted, valid source. So when we talk about cryptography on embedded systems, it's much less often that we're validating a user compared to validating a tool that's attached is a valid tool, is authorized, or a firmware update's authorized, or the device is operating in a valid environment, things like that. So ultimately what we're trying to force knowledge of is some secret key or some secret. And there's multiple ways this is done. The two we're going to look at, so the first one is called a message authentication code, or MAC. Basically what we have is we have an algorithm that the sender is going to perform on the message or the data, and this algorithm is often very similar to some of the symmetric cryptographic algorithms we're going to talk about. But basically what you can see is that the sender and receiver both have some secret key, and what we do is that the message authentication code is calculated by the sender from the message. Right, and note that this means the message could be in plain text or ciphertext, so the message does not have to be encrypted. We do not have to have confidentiality to get this message authentication code. And the receiver then performs the same algorithm with the received message with the secret key and confirms if they match. Right, so what you'll notice is this is actually providing two things for us. This is providing integrity as well as authentication, because basically the only way these two values here, right, the one sent over the wire and the one calculated locally, are going to match is if that secret key is also matching. So this assumes that anybody with the secret key is a valid user of the system. So of course this distribution of the key is very critical, because now we're saying anyone with that same key is a authorized user or authorized to send this message. Another way that's slightly nicer, because the issue with this and we'll look at this when we get to attacks, is that now we have some secret key that's in the same spot everywhere, right? So both the sender and receiver in this example have the same knowledge of the secret key. So the receiver, right, could also send a message or have a message and claim like, oh no, the sender sent that. And there's no way to prove that's not the case. So we'll discuss more about how this cryptographic, these public-private key systems actually work, but basically the bare minimum to understand is there's this form of cryptography where we have two keys. So we have one system. We have a private key that's only possible to perform some operations like decrypting. And the private key in this case could perform the other one, but isn't needed for it. The other key, the important part is there's a public key that is only possible to perform one operation, right? In this case, such as an encryption. And if you know the public key, you cannot perform the decryption. It's not possible to decrypt a message that was encrypted with someone's public key. So you can imagine this is really handy, because if I say, hey, can you send me an encrypted message? You can encrypt that message with my public key, but you can't decrypt it anymore even. No one can decrypt it except me. So this is a really easy way to generate secure channels over, totally unsecure methods. So there's a little more to it than that, but the basic idea is that we have this form of cryptography where we have private and public keys, as they call them. So it's called public key cryptography. And we have these two different keys. So why it's important for message authentication is that we can do this signing operation. And with the signing operation, basically, there's this example here, right, and it's often using Alice and Bob as normal, right? So we have a message. We perform a signing operation, which uses our private key. And the signing operation is normally actually taking a hash, so using the cryptographic hash function to generate a small chunk of data that we then encrypt or do something with that is performed in such a way that only us with knowledge of the private key could perform. So then what can happen is Bob, right, can perform a verify operation, and Bob can verify that this message that came from me actually has a matching signature, right? So the matching signature means that this message was created by someone who owns Alice's private keys. So this is the idea of public-private key signing. What's really nice about this is that the public key is basically something that you're going to have to trust. So if you want to say, I trust anything that comes from, like Microsoft, it means you trust anything that verifies with Microsoft's public key. So there's a whole other question of how you get that key there, right, of course. But for a lot of like IoT or small devices, we could consider the use case that it's actually just programmed into the device. So what we're going to see is lots of examples where the public key that's going to be trusted for some time is permanently in the device, or initially in the device at least. And basically any file that validates with that public key will then be used. And the only way a file will be validated with that public key is if it was previously signed with the associated private key. So this is going to be one of the really critical operations when we start looking at embedded systems. And this combines a few things, as I said, right? So it's going to combine the hashing functions, and it's going to use the hashing functions to then sign that hash so that you can trust, right? If you're given the file, you can calculate the hash yourself and then validate that the signature and the hash match, and therefore this file must have originated from whoever owns that private key that we have the associated public key for. So this is one of the ways that we basically combine everything to provide us with the required features of a secure system, right? So authentication is one of the most critical aspects of a cryptographic solution, but it's not like everything. It relies on all of them. So with authentication and integrity and confidentiality, it basically means we can now securely transmit a file such that no one can read it. We can trust the source of the file, so we know it's been published by whoever claims to publish it, and we know it has not been modified in transit. So you can imagine from this base, it gives us sort of everything we need to start building out a secure infrastructure, and a lot of security for not just embedded, really for everything is based on this. So what we're going to look at in the next few sections is some details of the algorithms themselves that are used so finally, after we have all this background, we can then get into attacks on the algorithms.